¿Quiere en español o en inglés? ¿O en mezcla?
Como se acomode más.
Pues a mí en inglés. Ok, si no hay problemas con ustedes. Okay, so last class, I was discussing the non-equilibrium thermodynamic foundations of the origin of life. And I gave you a theory which we have about the origin of life occurring on the surface of oceans and due to dissipative structuring with ultraviolet light in the UVC range. So we assume that we have only, for example, hydrogen cyanide, and now we know with the work of Claudette that we need also cyanogen, but cyanogen can be produced from hydrogen cyanide in the upper atmosphere with shorter wavelength UVC light. And so we need only water, hydrogen cyanide, cyanogen, and then we can produce all of the bases of life. We have only done that so far for adenine. We're working now with Claudette for guanine, and then we will do cytosine and thymine. So anyway, that was the first part. That was the first part of this thermodynamic theory, which is the dissipative structuring of the fundamental molecules of life. And we believe that we're going to be able to do that for all of the fundamental molecules, not only the nucleic acids, for example, also the amino acids, particularly those amino acids which absorb in the UVC range, which are the aromatic amino acids. So once we have these molecules floating on the ocean surface, then we assume that also they can be forming these single-strand DNA structures, especially at high temperatures. They will be in single-strand, not in double-strand. And it has also been shown in the laboratory, in fact, that you can phosphorylate the nuclear bases. That means attach the sugar and the phosphate groups, the three phosphate groups. You can attach them to the nuclear bases using ultraviolet light, and especially this UVC light in this range. So then we have these phosphorylated nucleobases, and they will stack one on top of the other because of the pi interactions between the bases. So these are like van der Waals interactions between the bases. They will stack one on top of the other. And then with ultraviolet light, you can form the bonds between the phosphate groups and the sugars to form the backbone. That has been shown, in fact, in the laboratory that can be done. So we don't have to do that experiment. So then we have these single-strand DNA structures which are floating on the ocean surface. And as the ocean surface temperature was cooling, then at night, they could find their complementary base pairs. For example, here in this region, we're reproducing the single-strand structure and producing two double strands where we have one single strand. And that was dissipative proliferation. Okay, so yesterday, I basically went through this very rapidly, dissipative selection, because we were running out of time. So today I'll talk a little bit more about it in more detail and a little bit slower. So if you have any questions on this dissipative selection, then stop me during my talk, okay? I also like to hear from you because then I know that you're following me. So we talked about dissipative structuring, which was the first component of the theory, and then dissipative proliferation, which was what we showed here. We have proliferation 2, where we had initially 1. And now we're going to talk about dissipative selection. That is giving rise to evolution. So that means selecting those molecules or those complexes of molecules which give ever greater dissipation. And so to understand that, we have to take a little bit of classical irreversible thermodynamics. And in the second part of the talk of today, I'm going to go over the specific details of classical irreversible thermodynamics. But for now, I'll just mention some of the details necessary to understand this. First is the entropy production per unit volume. Okay, we write that P over V, or sometimes as DIS by dt. The small I here refers to the internal production of entropy in the system due to irreversible processes which are occurring, okay, divided by the volume. And Prigogine has showed that can be written as a sum of forces times flows. So for example, in the case of the flow of heat, which is an irreversible process, we know that heat flows from hot to cold, and it doesn't flow from cold to hot. It only goes in one direction, so it's an irreversible process. We know that the force for that irreversible process is the gradient of 1 over the temperature. So it goes like 1 over T1 minus 1 over T2. And the flow is the flow of heat. And the multiplication of those two, X times J, gives the entropy production. Okay, that is for the case of the irreversible process of the flow of heat. But we also have other irreversible processes, for example, chemical reactions. And for chemical reactions, the force is the affinities over the temperature. The affinities depend on the chemical potentials, which we're going to see today a little bit later. And the flows are the rates of the reactions, or the velocities of the reactions, the V. Okay, and then we sum over all reactions which are occurring within the system. And that gives rise to the entropy production due to chemical reactions taking place within the system. And we know that the entropy production has to be positive definite for all irreversible processes. Okay, only in the case of equilibrium, we have 0 entropy production and the entropy is a maximum. So the fact that we can write the entropy production of the force times the flow means that we can divide the entropy, the change in the entropy production per unit time as dxp plus djp, where this dx refers to changes due to changes in the forces. And J refers to changes in the entropy production due to changes in the flows. Now, what Prigogine and Glanzdorf have shown that there is such a thing called a universal evolutionary criterion, which is written in this form, that this part, dxp by dt, has to be less than or equal to 0. So this is saying that the change in the entropy production due to the changes in the free forces in the system. So the free forces are the forces which are not fixed over the system, because we have some fixed forces. For example, in the case of the heat of flow, the fixed force is the gradient of the temperature. And in the case of the chemical reactions, fixed force are the net affinities in the environment and inside the system. So in the case of the free forces, okay, the variation of the entropy production in time due to changes in the free forces has to be negative definite. That's known as the universal evolutionary criterion, or sometimes called Glanzdorf-Prigogine criterion. But that doesn't say anything about the entropy production of the system as a function of time. It only says about that part which is due to the changes in the free forces. Because the change in the system is due to this part due to the free forces, plus another part due to the flows which are occurring within the system. And this can be either positive or negative, so we can have either positive or negative, or a reduction in the production of entropy, or an increase in the production of entropy. So it depends on this part. But this part, we can show that for the case of autocatalytic photochemical or chemical reactions, this tendency is to be positive definite. And so we get the total entropy production in greater, in fact, than this part, which is negative definite. Then we get the total change in the entropy production per unit time being positive definite. So the tendency is to increase, although this is statistical because it occurs at a bifurcation. If you remember, if we have a nonlinear system between the flows and the forces, in that case, we can have two solutions to the same equation. And these two solutions can have different entropy production. And we gave the case or the example of the Barnard cell. And the Barnard cell has two stationary states, or two solutions. One in which the hot liquid is coming up in the center of the cell and then going to the top of the cell and cooling off at the top and then going down around the edges. But we also have another solution which is a lower entropy production. Okay, so that corresponds to this other branch here, which corresponds to the case of the hot liquid coming up around the edges of the cell, cooling off at the top, and then going down in the center. So there are two different stationary states available to this non-linear system, and they have different entropy production. And which one does nature take? Well, it takes this because of this tendency, especially in these autocatalytic systems. And I've shown that, in fact, in one of the articles that I published, this article here in Entropy and last year. You can look at that article if you want more details. But the tendency is to go up in entropy production, but sometimes you can go down. So it's a statistical fluctuation which depends on the macroscopic occurrences. So we have, in fact, both deterministic and probabilistic effects in these nonlinear systems. So we cannot really treat it by statistical mechanics. So this was, for example, some of the stuff that Jeremy England has done, is trying to treat the origin of life through statistical mechanics, but we don't get that. You need both the deterministic and the probabilistic components if you want to explain the origin of life or life in general. And in fact, Prigogine, took the approach of Jeremy England in the 1960s, and he showed that this approach was not sufficient. So you can find that in Prigogine's book, Prigogine, Glanzdorf, and Structure, Stability, and Fluctuations. So we have to take into account that we have both deterministic, which are given by the equations, and we have probabilistic due to the fluctuations at or near to a bifurcation. And the example I gave of dissipative evolution is the dissipative selection of adenine. Okay, so this is dissipative.
Sir.
Yes.
Sorry.
No, see.
Can we look at the previous slide?
Okay.
Please. Then, what is the relevance of the universal evolution criterion of Glanzdorf if
okay.
at least we have the dp over dt?
Yes.
Like,
okay, well, we have to obey this. This has to be obeyed. This is one of the criterion. It's almost like the second law of thermodynamics, that for any system, okay, the entropy production, the changes in the entropy production due to the changes in the forces has to be negative definite. And we're going to see, in fact, in the next section of the class, that in the case that we have linear systems, okay, not nonlinear, but linear systems, then this also implies that djp by dt has to be less than or equal to 0. So that would say that the entropy production per unit time of the system has to always decrease. And that is the case for linear systems. So in fact, the system goes to a minimum of entropy production, not to a maximum. It doesn't increase like in this case. This is the case for nonlinear relations between x and j, where we have more than one solution. But in the case of a linear relation between x and j, then this criterion gives rise also to the fact that this has to be less than or equal to 0, because in fact these two components are equal to each other. You'll see that in the book of Prigogine. It shows that these two parts equal to each other. So in the case of a linear system, this is very important. It's a new result, if you like, from thermodynamics of nonlinear, non-equilibrium systems, is that the entropy production per unit time, so this component, the complete component here, has to be negative definite. It goes to a minimum, not to a maximum. Okay, but for our case, in the case of nonlinear systems, then we have to obey this, but it can be that this part, this djp by dt, is greater than 0, and it's such that it overcomes this part, increases the production of entropy per unit time, and that appears to be what is happening in nature for these systems which are autocatalytic. So for example, dxp can be less than 0, would mean that we are forming these molecules, okay, So these molecules, so the affinities for these molecules, because for the chemical reactions, we talk about affinities, are going down in time. Okay, so the chemical potential is reducing, but that's giving rise to a greater dissipation because of this flows. The flows are increasing. So in the case of our photochemical reactions, we're increasing the flows of the photons through the molecules, because these final molecules like adenine and guanine have this conical intersection, which allows them to dissipate very rapidly photons. So once these are produced, then we don't get much changes with the affinities, but we get an increase in the flow due to this part. So this increase is greater than this negative decrease, and that leads to dP by dt increasing. Okay, maybe it will become more clear when I give the second part of this talk today, which is about classical irreversible thermodynamic theory.
Okay.
Okay, so this part has to be always for any situation. That's why it's called universal. No, for any situation, linear, non-linear, far from equilibrium, near to equilibrium, this is always obeyed. Okay, but for non-linear systems, then we can have it that this part is different from this part. Okay, in the case of linear systems, the two are the same, and that's why they both have to be negative, and this becomes negative definite. The entropy production decreases in time. But for non-linear systems, this part can become positive, okay, and it can become so positive that it overcomes this negative part and produces this being positive definite. Okay.
Okay. Professor, the tendency of autocatalytic photochemical or chemical reactions is
Yes.
is a value that is, I don't know, esa desigualdad se obtuvo como que ya está, cosa como comprobada así, o es como parte de una hipótesis para obtener el resultado. No sé si me explico, o sea, ese dp sobre dt mayor o igual que cero.
Yes, it's been, for example, I think it's in chapter 6 or chapter 5, maybe even in the book of Prigogine, where he talks about nonlinear systems. And he gives an example, in fact, for autocatalytic chemical reactions. And he shows that this part becomes greater than this part. And so positive production of entropy. So it's been shown for chemical reactions. And we can do the same for photochemical reactions, just by taking into account the flow of the photons which are going through the system. Now, in the case they are being dissipated directly into heat through the conical intersections, that is like an increase in the dissipation of the force, the fixed force of the system, which is the photon potential. Just like in the case of autocatalytic chemical reactions, where the force of the system are the net affinities of the system because of the chemical potentials of the different reactants involved in the system. Okay. So
yeah, and it seems curious like that. It seems curious that it's like the acceleration of entropy. Like, I don't know how to say it, because it's
the increase in the production of entropy.
Yeah, because it's over time and then over time again.
Yes.
It seems a little curious to me, but okay, I think I
Yeah.
understand.
Yeah, it's a very important, because it leads to evolution. No, so evolution that we see today in nature is due to this fact that this becomes positive definite in general, not always, as I say, that it can go down because it depends on a fluctuation. But in general, this is positive definite, and that is what gives rise to evolution, that we do have these positive feedback systems, these nonlinear systems in nature, and they are allowed because they don't violate any fundamental laws of nature, neither the second law of nature, neither the universal evolutionary criterion of Prigogine. And so, but they are this like autocatalytic, and that leads to increases in entropy production, or what we call evolution of the system. No? So we get to biospheres of ever greater dissipative efficacy. Okay. Okay, so the example I'm going to give today of dissipative evolution is also the same example that I gave of dissipative structuring. But I just want to show you that during the structuring process, we go from systems which do not dissipate much photons to systems which dissipate very strongly photons. And that if we look at the system macroscopically, that is not at these individual molecules or these intermediate molecules, but we look at the concentrations of these different molecules, okay, in the system, we can see, or we can imagine, if we have nonlinear systems, that we can have different solutions. That is to say, we can have different concentration ratios as a function of time. Or at a given time, we can have 2 or 3 or whatever number of different concentration profiles of these molecules in the system. And some of these profiles give greater dissipation of the incident photon flux, and some of them less. But the tendency of nature is again towards those which produce more dissipation, those concentration profiles which produce more dissipation. Okay, so to show that, we have this system then of equations giving rise to adenine from 4 or actually 5 molecules of hydrogen cyanide, because we add another one at the end here. So we have this set of chemical reactions. Now these chemical reactions correspond to each of these. For example, these are photochemical reactions which are occurring, and then we have chemical reactions. And then we have, this is another chemical reaction here with HCN. And then we get to these molecules which are very dissipated. So this is the list. There's actually 16 here for the production of adenine. And there are only 7 here, reactions listed here. But we have to take into account those reactions which are also in competition with the reactions to produce adenine. And some of those reactions in competition are, for example, hydrolysis. That means the adding of water molecule to hydrogen cyanide, which is represented by H here. So we, just to make it more convenient, we have a symbol which represents these different chemicals, these different molecules. So H represents hydrogen cyanide, and it goes to formamide through hydrolysis. And we have a rate equation which we found in the literature. Okay, these are the references. And we also have the formamide can go to formamidic acid through the absorption of a photon at 220 nanometers. And so for these photochemical reactions, what we have instead of these reaction rates, we have quantum efficiencies. That means for every photon absorbed, how often does it go this reaction? So from formamide to formamidic acid, every time a photon at 220 nanometers is absorbed, and these are the quantum efficiencies, which have also been determined experimentally. Okay, so we do that for all of the reactions which are occurring here, and also the reactions which are in competition. And there are chemical reactions and there are photochemical reactions. And so there are about 16 important. There's in fact many more reactions which are occurring, but we've deemed them not to be very important. That is that they don't affect very importantly the final concentrations of adenine or the concentrations of the intermediate molecules on the route to adenine. So we have these equations which represent the photochemical and chemical reactions, and our system consists of a vesicle. Okay, so these are fatty acids, double layer wall vesicle, and we have photons over the system, and we're absorbing these photons on HCN molecules, hydrogen cyanide molecules, and they're gradually producing other molecules, which are these molecules here, until we get to adenine. And adenine is very stable because it takes a photon and it dissipates it directly into heat without any photochemical reactions. So the quantum efficiency is almost equal to 1 for adenine. That means that it always goes to the ground state without further chemical reaction occurring. So that's why it's very stable under this UVC light. And the system is that we have these molecules, initial molecules in water under ultraviolet light and floating in this vesicle at the ocean surface. And we follow the system, the concentrations determined by these reactions which are occurring. We do this over 30 days and we follow the system. And at 10 days, we include a perturbation. And the perturbation, the idea of the perturbation is to take the system from one stationary state to another stationary state. So in this case, we perturb the system by increasing the concentration of hydrogen cyanide in the environment to 0.1 molar from a value which is about 10 to the minus 4, 10 to the minus 5 molar. We increase it to 0.1 molar, 10 to the minus 1 molar. And we have that perturbation only lasting for about 2 minutes out of 30 days. So only 120 seconds. And that is enough to allow us to go into a new regime or a new stationary state with a greater photon dissipation rate. Okay, and that changes the concentration profiles of the molecules involved in the reaction to adenine. So this is the set of equations, including the fusion, and this is the rate of change of, for example, hydrogen cyanide as a function of time. These are the chemical reactions, and these are the photochemical reactions. Yes?
Sorry.
No,
excuse
sure.
me.
No, excellent that you're asking questions.
What in nature can be like the perturbation in real nature, like something,
Okay.
what's happening?
Yeah, okay. Well, in real nature, what happens if you put hydrogen cyanide in water, it accumulates into little patches. Maybe you've seen patches of oil. For example, when there's an oil spill on the ocean, we get patches of oil. Okay. I think we're going to be cut off in about 5 minutes. Okay. So if we'll come back to it. So these hydrogen cyanide molecules have a small dipole moment, and that makes them come together, and they can float on the ocean surface because they're lighter than water, just like oil is, and they can form these patches. ¿Sí? Áreas pequeñas en donde hay un aumento en la concentración, como igual que pasa con aceite, flotando en el agua. So we assume that in nature this would correspond to just to a patch of hydrogen cyanide, increase in hydrogen cyanide, but we assume that the vesicle only passes through it in about 2 minutes for 2-minute perturbation. And that is what's causing these changes in the concentrations profile. So this at 10 days, we have this increase from this value of hydrogen cyanide. It increases to 0.1 molar concentration. And that gives rise to a change in the concentration profiles of the different molecules in the system. So it's like we perturb the system into a higher entropy producing state, just like in the case of the Bernard cells when we went from one stationary state to another, which was higher entropy production. We're doing the same now, but for photochemical reactions. So this is the case in which we have the perturbation. This is the case with no perturbation. And you see that we increase maybe 2 or 3 orders of magnitude with the perturbation, only 2 minutes of a patch of hydrogen cyanide. Okay, and if we will look at the entropy production, so these are the concentrations of the different molecules, and we know that these molecules are absorbing photons, and we know what the extinction coefficient, or the molar extinction coefficient, that means how many photons a mole of this molecule in water will absorb. Then we can calculate what is the entropy production based on the dissipation of those photons into infrared light. And if we do that, then we get this graph. These spaces here correspond to nighttime when there are no photons. So then we have no production of entropy because we're not dissipating photons. So only during the day we're dissipating photons, and we'll get to about 10 days, we do this perturbation, then all of a sudden the entropy production increases. And this is the case for the same system, but without the perturbation, 10 days. Okay, so we're staying in one stationary state here, and this is the case where we have promoted the system into another stationary state of higher entropy production, which corresponds to a different concentration profile of the intermediate molecules. Here we have a different concentration profile than we did before the perturbation. Okay, so let me just conclude because we're going to run out of time in about 2 minutes. So life's thermodynamic function then is to convert sunlight into heat, which is known as dissipation. That's what it's doing today with the leaves in the plants. the pigments in those leaves, which are absorbing sunlight and dissipating it into heat. And we're assuming that it also did the origin of life, but in the UVC range, because we didn't have the biosynthetic pathways, the complicated biosynthetic pathways to produce these pigment molecules. But we did have ultraviolet light at the beginning of life, and that ultraviolet light in the UVC could form these pigments in the UVC, which are the fundamental molecules. And we show that most of the fundamental molecules absorb very strongly in this UVC range, just where dissipative structuring is allowed. And I showed you that we can have dissipative proliferation in the system. So we get 2 molecules of DNA where we had 1 through dissipation also for the denaturing. And I just gave you the example of dissipative selection, of selecting these different concentration profiles, which are available to the system. And we can go there through a perturbation of the system. Okay, and so then this is then the non-equilibrium thermodynamic elements for explaining the origin and evolution of life. Of course, this is one theory, but I think it's the most complete theory that I have seen. So I'm not trying to blow my own horn, but anyway, the other theories for the origin of life are very vague theories. So we have to find a theory which is based on dissipation, because all irreversible processes, and life is obviously an irreversible process, depends on dissipation. So I think this theory